Hello, welcome back to Piers Rocks. Today I'm setting aside the disk drives to do some USB programming on the Raspberry Pi Pico. So before you think I'm abandoning my disk drives, I do have a disk drive related project in mind for this Raspberry Pi Pico. But I spent the last couple of weeks playing around with the Pico SDK's USB support in the form of the TinyUSB stack, although at times it's felt more like fighting than playing. TinyUSB itself has very little documentation, and there's very few example implementations of a custom USB device out there, which is what I want to develop. So now I've got a basic custom device implementation working. I've uploaded it to GitHub and wanted to go through how you actually implement a custom USB device on the Pico with TinyUSB. If you want to follow along at home as I go through it, I've put the link down in the doobly-doo to the GitHub project that you can check out and compile and flash the firmware to your own Pico to your heart's content. So let's get to it. First of all, what do I mean by a USB custom device? So there are a number of different classes of devices in the USB specifications. Human interface device is one class, CDC, a communications device, is another class, and they follow particular sets of protocols. So if one vendor implements an HID, a human interface device, and another one does, or an audio device, for example, then they may well be interchangeable in terms of functionality. When I say a custom device, I'm actually talking about a vendor class device. That's one where there is no particular detailed protocol that the device actually supports. The vendor can choose what protocol they want to implement, so long as they stick within the very high level USB specification. They support control transfers and bulk transfers and the standard USB communication mechanisms. So that's what I'm talking about when I talk about a custom type of device. Now, before I actually go through the code and we look at how to build a custom device in TinyUSB for the Pico, I thought I would download and build the code and just demonstrate the device working. There's a few prerequisites that are in the README for this project that you need to have installed first, in particular the Pico SDK, which I've got installed, and I've also got the ARM compiler installed on this system. So first thing I need to do is I need to clone the project. Then I go into the project, I make a build directory, I go to the build directory, and then I cmake ... That uses the cmake lists.txt file in the root directory to create a bunch of make files. I can then make it like that, and within a few seconds the project's built. So I can load this onto my Pico device, which I have here. Now I've got the UART for this device connected up to a USB to serial device, so I can actually look at the debug logs coming out of this Pico, and I've got a second window here where I'm looking at the serial port. So I'm just going to connect this Pico up to the Linux PC that I'm using. So that's connected now. You can see there's nothing on it, at least there's nothing producing any debug output. And if I look at dmessage, you can see that it's detected that a Raspberry Pi in bulk storage mode has been connected. This means it's ready to flash. So I can flash the image that we've just built like that, and then I can also, well, I'll just do the flashing. So that's now flashed the example image to the Pico. I now need to reboot it, which I will do like that, and quickly switch over once I've done that to the serial output. And now we see output from this example coming out to the console. So we've successfully built the example and downloaded it to the Pico. Let's see what we can do with it. So there's a bunch of scripts as part of the example that allow you to communicate with the device. These scripts essentially just wrap a very low level commands, USB commands like control transfer commands and bulk transfer commands, the standard fundamental primitives of USB communication. As I said, this is a custom device. It's got a custom protocol. So first thing I'm going to do is send it a custom initialize command. Okay, so that I can see that succeeded because it's given me what I expect in terms of the response. 8 bytes of data, 8 is a magic number, and 3 is also some kind of return code from this device, and all the rest of the zeros is fine. If we go and look in at the serial output, we can see that we received what looks like 3 different control transfer messages over USB. That's essentially the way that TinyUSB serves those the single control transfer to your application. It does it 3 times, but we can see it received that initialized command. Next thing I can do is I can query some information from the device like that, and we can see that this is the Git revision of the code I used to build this image. This is the GCC version that I used to compile. You can see I'm using GCC 14.2.1, and this is the Pico SDK version that was used to build the example. Now those were both control transfer, USB control transfers. We're now going to do a bulk write. This is going to write a 4-byte command to the device and then 2 bytes of data. We should get a 3-byte return code back. So we did get a 3-byte return code back. 02 means success, and then 0200 is the number of bytes that it read, the device read, that I sent it after the 4-byte control command. So that's in little endian format. So that's the right response. And then I can read some data from the device. I'm going to ask it to send me 64 bytes of data. It's just going to send me all X's as the data. And we can see we received 64 all X's in from the device. So the device is doing everything that I've expected it to do. The other thing I'll show you is that this is actually being recognized as a custom device by the kernel. If we look at dmessage, we can see when the Pico rebooted after flashing, we can see it disconnecting there, and then we can see the new device, or the device with the new firmware being detected, and we can see it's got my product ID, it's got my manufacturer, and my serial number associated with it. We can do an LSUSB to list the devices attached to this PC, and again we can see this custom device being listed here. And then we can actually look at the detailed USB information if we do S and then the bus and then the device, I think in that format. So this is all of the what's called the descriptor information that the USB device has supplied the operating system. Again, we can see the manufacturer and the product ID within here, and then a bunch of additional information. So this, to people who understand USB, shows you what types of capabilities the device has. Now we've seen it working, let's look at the source code, see how you actually go about building a custom device implementation like this. So you can see the 4 source code files that are part of this example. It's relatively straightforward to get to grips with this implementation. The first file I'm going to look at is the TinyUSB config.h. This is actually included directly by the TinyUSB stack, and it configures the various capabilities and features of TinyUSB that you want to have as part of your application. So it's really important that you get this right. It looks quite complicated, this header file, but really a lot of it's boilerplate, and there's only a few things that you really need to make sure you get right, and that's you need to have this config TUD enabled set to 1. So this stands for TinyUSB device, as opposed to TUH, TinyUSB host, because we want to create a device, not a host in this example. Second thing that's really important are these vendor configuration settings. You need to have config TUD vendor set to 1, so TinyUSB knows you want to have a vendor implementation, and then you need to set some buffer sizes to allow the communication to and from your implementation to work over the USB bus. And then the final thing just to flag is that there is a debug setting here, and if you set this debug setting to more than 0, you'll get some debug logs out of TinyUSB via UART. But you need to be quite careful with this, because it does slow down the USB stack, and you may end up USB requests may end up timing out as a result of turning this on. I found adding targeted printfs to the TinyUSB stack is actually a better way of debugging it than changing this setting. And that's really all you need to know about a TinyUSB config.h. The second file I'm going to look at is the USB descriptor.c file. So we looked at the USB descriptors with LSUSB a few moments ago. So these are the properties that the USB device has, and when the operating system detects that a USB device has been plugged in, it attempts to communicate with the USB device and find out what capabilities it has, what its properties are. That is done with things called USB descriptors. There's really two descriptors. There's a device descriptor, so something that describes the entire device, and then there's a configuration descriptor. You can potentially have multiple different configurations that your device can be in, although I think most devices only tend to have one. So you have this device descriptor, which has a bunch of high-level properties of your device, and then a configuration descriptor, which has more detailed information within it. They're all supported here within this USB desk.c file. First of all, we can see the device descriptor. So it has things like, this is a device. This supports USB 1.1. If you wanted to support 2.0, you'd just say OX0200 here. It's a vendor-specific device class, so that's what makes it a custom device. It has our vendor ID and our product ID. I'll show you what values these have in a moment. They're in the include.h header file. All of these, many of these hash defines are. And then there's a pointer, basically an index into an array for the manufacturer information, the product information, and the serial information. That's kind of the key information that's stored within the device descriptor. And then there's a callback here. And you need to implement this callback within your application, and TinyUSB will call this callback when it needs to have the device descriptor, and you serve that descriptor up. You can see here I'm just providing a pointer to that structure that I've just run through. That's all this callback needs to do. You could do a bunch of dynamic stuff in here. You don't need to have a fixed construct that you pass back, but you need to be really careful dynamically changing information associated with your USB device. If you change its properties, then the operating system tends to cache those properties, and if you plug it back in with different set of properties, it may well choose not to reread those properties, and you have to go through a bit of rigmarole to clear the cached information the operating system has, so that your operating system will read your new properties. It can be easier just to change the vendor ID or product ID of your device, so that the operating system thinks it's a completely new device that's been connected. But this is all you need to do. You need a construct, and then you need a callback returning that construct. The second thing you need is you need a configuration descriptor. Now this is actually a lot more complicated to build up, and TinyUSB provides a whole bunch of macros to make this easy for whatever type of device you're trying to create. The first thing you need is a TinyUSB config descriptor, and then you need, in our case, a vendor descriptor that says that this is a vendor device. You can think of this first one essentially as a kind of header, and it has a control interface defined within it, so that all control transfers go to this interface. And then we have our vendor implementation that defines the interface for this vendor implementation, and then the endpoints within this implementation. So endpoints and interfaces within USB. Endpoints are things that the host will actually communicate with to send large amounts of data to and from. And each endpoint is either an out endpoint or an in endpoint. These are described from the perspective of the host. So an out endpoint means sending data from the host to the device. An in endpoint means receiving data from the device to the host. Hopefully I got that the right way around. Which is really confusing when you're implementing a device, because these are labeled the opposite way around than that you'd think. Out is to the device and in is away from the device. And then endpoints are grouped within interfaces in USB, and we're defining a single interface for our vendor implementation that those two endpoints are part of. I believe that endpoints are still unique within the entire USB device, despite the fact they are contained beneath a particular interface. That's all you need for your descriptor configuration. Now I have an array which essentially provides a mapping from the indexes for the strings that we saw earlier into actual strings. So this is an index of 1, for example, and this is an actual string that says peers.rocks in the header file we'll look at in a second. And then this next function is a callback to provide the configuration descriptor that we've just looked at. Again, it's just providing a pointer to this descriptor configuration here. And then finally, we have to provide a callback that actually allows TinyUSB to take the indexes that were in the descriptors and find the strings for those. So that's what this particular callback is doing. Is it's saying, if I get requested the serial number string or the manufacturer string or whatever, I will look it up in my array, then it's converting that into UTF-16. USB deals with UTF-16 strings rather than UTF-8 strings, so all characters are 2 bytes long. So this is a little bit of code that does that conversion. That's it for the USB descriptors. That's what allows the operating system to recognize this device and enumerate the device. You can see it in LSUSB under Linux. You can look at the details of what that USB device supports. That's all supported through this relatively small amount of code. So we'll now take a quick look at the include.h header file. First of all, we can see my vendor ID and product ID for this USB device. Every USB device has to have a vendor ID and product ID, and that's unique to that manufacturer's implementation of that device. So all Raspberry Pi Picos have a unique vendor ID and process ID. That's unique as in no other device other than a Raspberry Pi Pico will have that vendor ID and product ID when you plug it in and try and flash it. So the operating system knows what it is, looks at its device descriptor, and you can mount it as a file system and so on. So you need your own ones of those for your own USB device. These are not assigned to me. I've just chosen some random, hopefully unassigned values. But every device of a particular type will share the same vendor ID and product ID. So all of the Raspberry Pi Picos, when in firmware update mode, have the same vendor ID and product ID. It's only unique to that particular manufacturer and that particular manufacturer's device. We have some buffer size definitions for the endpoints that our device supports, and we can actually see the values of the strings that we saw in LSUSB, and the callback we looked at a second ago is actually accessing, is using these values for the strings it provides. We can see the string IDs that we used in the descriptors, and we can see the interface numbers that we've used. And then we can see our endpoint numbers. In endpoints are always ORed with 0x80, so bit 7 is always 1 for an in endpoint, and an out endpoint, that is always not set, that bit. Got some debugging, logging macros, and then I have a bunch of constants that are part of the custom protocol that I've implemented on my device. That's not really interesting for this video. I'm not going to go into this protocol in too many details, but this is what allows me to send it commands like the initialize command and get the git revision that it was compiled with and so on. That's all provided here. I can indicate that I want to read data, or I can indicate that I want to write data to the device. So this is my custom protocol implementation within my example. For if you were implementing your own vendor class, your own vendor device, this would probably be entirely different for your implementation. So then the final file to look at is main.c, and this, as you'd expect, is where most of the interesting stuff happens. We've got a bunch of header files that we're including: Pico header files, TinyUSB header files, I have a little typo there, I'll fix that, and our own header file that we just had a look at. I've got some forward definition of some functions I'll use later. I'm not interested in those, we won't go into those. Let's look at the main function. So this is very standard in a Pico. We're initializing std.io. This allows us to do things like logging to std out and for it to be picked up by the UART that we're also enabling here. We're logging some information. We saw that in the serial console output. If we go and look back right up at the top, I don't know where it was. There it is, TinyUSB vendor example started. Now in this example, I'm starting a watchdog. This means that if I don't kick the watchdog within 5,000 milliseconds, 5 seconds, then the device will assume that it's hung and will reboot itself. That's pretty standard good practice when developing an embedded device to make sure it doesn't just lock up. I'm also using some of the multi-core functions in this example. You don't need to do this, but you may want to run all of your USB handling on core 0, like this example is doing, and then you might want to have some business logic, logic that's custom to your device running on core 1. This is how you would do that. You call multi-core launch core 1, you give it a function to call. All this function does is it logs periodically and it feeds the watchdog, because with a watchdog running you have to feed it on both cores. If you don't feed it on one of the cores, it will reboot after the timer expires. Then I'm initializing TinyUSB. There's a Pico specific board init function within TinyUSB, which I don't think you have to call. In the standard case, in my case, I don't think this is doing anything, but it's good practice to include it. And then you initialize the main TinyUSB stack here. So that's all of the initialization out of the way. And you can see this main function has a very standard pattern. It does a bunch of initialization, then it goes into a while loop forever. This is how you implement pretty much every embedded device. So what do we do forever? Well, first of all, we go into a function that's really all it's doing is logging periodically that we're in this main loop. The second thing it's doing is it's calling TinyUSB device task repeatedly, constantly. We'll come back to that. We are seeing whether we need to send any data out to the host. Again, we'll come back to that a bit later. And then we're feeding the dog. And then we're doing it all over again and again and again. So let's talk about TinyUSB task. So the way that TinyUSB supports USB is that it registers with the hardware registers within the Pico for interrupts to fire when appropriate USB data, for example, targeted towards the configured interfaces and endpoints on the device that we've configured. When the hardware receives packets for those endpoints and interfaces, a TinyUSB interrupt is called immediately because it's an interrupt. And then TinyUSB queues some work on a queue to be done later because it doesn't want to do all of its work in an interrupt. You just do the minimum possible in an interrupt and you queue the work for handling later. This is later. TinyUSB task is later. So you have to continually call this so that TinyUSB can go through and process the work that it's put on its own queues. And TinyUSB will call into our application using a set of different callbacks. And that's really the most interesting part of this example of the TinyUSB callbacks. So let's take a look at those now. In this example, a bunch of the next code is the protocol handling. So I'm going to skip past this because it's really just specific to my particular example. So here we're now in the TinyUSB callbacks section. The first set of callbacks you might receive are TinyUSB device mount callback, unmount callback, and there's also suspend and resume. So mount callback is essentially once the operating system has communicated with your device, figured out what it is, and decided, yes, that's okay, we can talk to that as an operating system, it will call the mount callback within your implementation. Now, you don't have to implement many of the TinyUSB callbacks, so you don't actually have to mount callback. If you don't have anything to do, don't implement it and it will still build and compile and work perfectly fine. In my case, I'm initializing my protocol handling support in these callbacks, but whether you do that or not will be dependent on your implementation. I think the only callbacks you actually have to implement, although I've not checked this, are the descriptor callbacks, because if you don't implement the descriptor callbacks, I don't think TinyUSB is able to provide the operating system it needs with the information to enumerate your device and actually decide that it's going to mount it. But everything else, you have an option whether you want to implement that callback or not. And you can see in this example, there's plenty of comments explaining why you might want to implement a particular callback and what you might want to do in that callback. So anyway, mount callback, unmount callback, suspend and resume. We'll skip past now. We'll come back to TUD vendor RxCB and we'll go on to TUD vendor control exfer CB. So this is the callback that is called when a control transfer comes in for your implementation, for your vendor class. And this is actually this took me quite a bit of time to get my head around how to support this function. So there are a number of different stages of control transfers. There's setup, data, ACK phases. And TinyUSB will actually call you for each of those 3 stages for each control transfer. Control transfers can also be either in direction, coming into the host on the device, or out direction, going out of the host to the device. That's really talking about which direction data needs to be transferred. The host is always sending the control transfer to the device, and the device is doing something as a result of that. But the in or the out means, is the host going to send some additional data if it's out, or is the device going to send data back to the host if it's in? So with TinyUSB, if there's a control transfer that's directed at your particular device class, then you need to handle it in the setup stage, and you need to return data. If there's data to be returned, if it's an in direction, you need to do that within the setup stage. So let's go and take a look at how we do that, and I'll fix another typo on the way. Right, my code's riddled with typos, always is, always has been. So I'm doing a bit of logging, and I'm doing a bit of checking to see whether we need to actually deal with this particular type of control transfer. A lot of control transfers, the sort of standard spec ones, TinyUSB will deal with it on your behalf, so you don't need to deal with it. But TinyUSB will still provide it to you in case you want to do anything with it. So I only want to deal with it if it's directed at my interface, my vendor interface, and we saw that I set that index up previously. So I now look at the stage, and if it's control setup stage, this is where I do all of my logic. And I look at the request byte that's part of that control transfer, and I decide what to do as a result of that. So control echo, which is 0, just echoes 0 back again. And this is an in request because it needs to, the device needs to echo information back in to the host. We actually saw me running the init command earlier. That is also an in control transfer because we received 8 bytes of data. And you can see when I receive this, I'm just doing initialized protocol handling. Let's look at some others. I actually have a control command that will let the Pico, will command the Pico to enter its bootloader mode. So I don't need to unplug it and hold the button down and press it back in to flash new firmware. Once I've got this firmware on the device, I can just send a control transfer with the appropriate value set, and the Pico will actually enter into the bootloader code itself. And then you can see we saw the response from the Git revision and the GCC version and the Pico SDK version. We can see where that's all handled here. Now each of these commands that's sending data back is filling in control response and setting a length of data that it wants to return. And this is the most important bit of the entire function. We're calling TUD control transfer to send that data back to the host. So we're passing it control response and the length. And we're returning the return value of TUD control transfer, which should be true if the control transfer send succeeded. If it didn't succeed and it returns false, then this whole control transfer will be errored back to the host that sent it. And if you're not dealing with a particular type of control transfer or a different stage of transfer, you need to return true, otherwise the device is going to error that control transfer back up to the host. So that's the control transfer handling. The other piece we need to look at, and the final piece we need to look at, is the bulk transfer handling, which was the callback that we skipped over, and that's this TUD vendor RxCB. So you've got 2 main callbacks. You've got TUD vendor control transfer CB that we just looked at for control transfers, and TUD vendor RxCB. This is for handling bulk writes from the host to our device. Now I'm not going to bore you with the details of this implementation, this particular protocol that I've implemented, but essentially you get passed in data via this callback using the buffer and the buff size variables, and also what interface it came in on, and then you process that as you see fit. So I'm doing a bunch of manipulation and protocol handling here. When I want to send data back as a result of receiving a write bulk command, you use TUD vendor write to send that information back. And I'm passing a buffer and a length of data. And then you must call TUD vendor write flush. This actually causes the TinyUSB stack to send out, upload that information that you sent to the host. Otherwise, it may just sit on it waiting for some more data to come in before it sends it out. So you have to call TUD vendor write flush out. Now, if you're receiving data in this function, it came into your out endpoint, because remember, out is from the host to the device. When you send TUD vendor write, it will be sent using your in endpoint, because you're now sending it from your device into the host. So that took me a little while to get my head around. Now, there's no return code on this function, so you don't need to return true or false. You basically just handle the data. If you don't handle it properly, if you hit a bug, if you hit an error, well, you just drop it on the floor. That may or may not be fine based on your implementation. Now, there is one final function that's called within this callback, this read flush, and I don't know how important this is, but it's in the sole TinyUSB vendor example that's part of the TinyUSB stack, and it's within this hashif test, basically saying if you're using a FIFO buffer in TinyUSB, which it does if you set this to more than 0, you need to flush that once you've actually accessed the data from within it, which you did by accessing buffer and buff size in this function. So I'm keeping it in because I think it may well be quite critical to keep in. Now, there is also one final callback which I omitted before, which is TUD vendor TXCB. This is called back to you whenever the TinyUSB stack has actually sent data out to the host, based on your command by using TUD vendor write, which we saw earlier. This will call you back and say, yes, I've sent those bytes. And then once you've received that, then you may want to do some processing based on that. For example, I think you may need to keep hold of the buffer that you gave TinyUSB to send the data until it's been sent and you've received a notification here, and not reallocate it and not change any of the data. I don't know if TinyUSB is copying that data out as soon as you call its function to write data. But anyway, this gives you a notification that data has actually gone out and been sent to the USB device. And if you have a log here, you'll be able to see if you fail to call the flush function to actually cause the information to be written out. So that's really the long and the short of it. There are 4 files you need to implement. You need your TinyUSB config.h, which configures the TinyUSB stack. You need your USB descriptor C file, which is the key information the operating system needs to enumerate and mount your device. And then you need your main.c, and that's where you implement whatever callbacks that you want to implement. You don't actually, I've said already, you don't need to implement all of the callbacks. TinyUSB also does provide a number of different ways to do certain things. So we just looked at the TUD vendor RxCB for receiving bulk data. Don't actually think you need to implement that callback. You could, in your main loop, instead poll with the TUD vendor read function, and you can actually query whether there's any data available to read rather than implementing that callback. Your choice how you go about doing that. I hope you enjoyed that episode and found it interesting and useful. While TinyUSB had, at least for me, quite a learning curve associated with it, it's relatively straightforward once you get to grips with it. One thing I didn't mention when I was going through it is that TinyUSB provides a really quite high level API to your application to implement. It's much higher level than, say, Loofer, which is lightweight USB framework for AVR, for 80 mega for Arduino type devices, where that provides you with quite low level control to the USB stack. For example, you can do things like stall endpoints. Stalling an endpoint is basically saying I hit an error on this endpoint as part of my device, and stalling it signals to the host that something bad happened and the stall has to manually go in and clear that stall. There is no way using this high level API of controlling the stall state of endpoints. You can do it with TinyUSB. There are lower level APIs that you can call, private APIs. I went down rabbit holes for days trying to use those low level interfaces and ended up with very strange behavior. But if you did want more control with your USB device using TinyUSB, then you would implement your own device driver in place of the TinyUSB vendor device driver, which is what we've seen this example using. Anyway, with that having been said, if you're interested to see what use I put this Pico USB stack and how it relates to disk drives, please subscribe. Please join me for the next episode. Until then, rock on.